So in this video, we're going to work on defining logarithms and understanding what they are, as well as converting between exponential and logarithm forms. We're going to solve log equations, define logs to simplify expressions, define and graph the logarithmic functions, and then look at applications involving growth or decay. This is a lot of material to cover in a video, so please feel free to pause, rewind, and rewatch as necessary. So a logarithm is another way of writing an exponential value. So why do we have logarithms? Because logarithms help us solve equations with exponential values, and they also allow us to write very large or very small numbers with a very small amount of notation. So when you see y equals log base a of x, that's the same as x equals your base a, notice it's a base of the logarithm, base here, to the y. This is the way I remember it, students. Your base remains the base, and the x and the y switch places. If you think about it that way, if the y switches places with the x, then it looks like an exponent when it's in logarithm form, because that a is below the y, and then you get x equals. So that's a great way to remember it. So when we complete the swap, our a is the base, our y is the exponent, and then x is going to be what it equals. So this just kind of visually shows you that swap that happens with the x and the y switching places. So the meaning of a log is the exponent to which the base must be raised to get the answer x. So this is where things can get confused. X is a value you want to get out of raising a to some exponent. So if I have 2 to the 5th equals 32, the base is going to remain the base, and the 5 and the 32 are going to swap places. Same thing here. 100 to the 1/2, 100 is going to remain the base, the 10 and the 1/2 are going to switch places. Then I have my base, which is 6, the -4 and this are going to swap places. Now we can use a calculator to approximate the logarithm to 4 decimal places. Feel free to use the Web 2.0 calculator. However, you're going to notice that it's not going to allow you to do a base 2. The way you're going to evaluate this in a calculator is you're going to enter it as log 13 divided by log 2. So that calculator doesn't have the ability to change the base, I don't believe. Double check me on that, but you're going to write that as that way. So yeah. Then we're going to do the same thing with B and divide log 18 divided by log 6 because the calculator only has a base 10. Same thing in C and same thing in D. So you're just checking to be sure that you have those answers. Now to solve logarithmic equations, it's easiest to most often to write them as exponents. So what I did was I took this and I kept the base to base and I swapped the x and the y. Now it's simple to solve because you can enter 3 to the -3 in a calculator and get 1/27. And you can do that in Web 2.0 and it does give you the final answer as a fraction. And in B, you're going to do the same thing. The base is going to remain the base, and then you're going to swap. 1/3 squared is 1/9. You'll subtract 5 from both sides, or you can multiply by 9 first, whichever you're more comfortable with. So here I multiplied everybody by 9 to get rid of the fraction. I subtracted 45, and I divided by 18, and then I simplified. If you type into the Web 2.0 calculator 44 divided by 18, it's going to go straight to the fully reduced answer for you. So you should get that answer. We're going to continue in C and D following the same process. So the base remains the base, and then you're swapping sides of the exponent. To get x alone, you're going to take the 4th root of both sides. Since I can't have a negative answer in the base of a logarithm, I can exclude the -4th root of 5. In D, I'm going to follow the same process. The base stays the base. I swap things around, and I need to figure out how to get 36 to the x to be equal to the 4th root of 6. So I'm going to write 36 as the power of 6. I'm going to distribute the exponent, and then I'm going to set it equal and solve for x. So I get 1/8 because 1/4 divided by 2 is 1/8. So we have a couple of logarithm properties that help us progress through logarithms. If the base and the number next to it are the same, it's kind of like they cancel out. That's not mathematically what's happening, but it's kind of like they cancel. And then the base and the log and the exponent are the same, it's kind of like they cancel and we get r. If my base is the same, so like say this is log base 2 of 2, that's always going to be 1. And log of 1 is always going to be 0, no matter what your base is. So looking at these properties, look at the previous slide and try and figure out what they would equal using those properties. So A would be 1 because the base and the number next to it are the same. B would be 1 as well because the base and the number next to it are the same. And C, anytime the inside is 1, it equals 0. And D, anytime the inside is 1, it equals 0. In E, the log and the base cancel out because they're the same, and you get 7. In F, the 5 and the log 5 cancel out, and you get 6. And I use cancel out loosely because that's not mathematically what's happening, but it's just a great way to remember it. Log base 4 is 64. I'm going to rewrite 64 as 4 to the third so that I see that nice cancellation of properties. When I graph logarithms, we've already talked about exponential growth and decay. When I graph a logarithm, I can recopy it as its exponent, and then I can sketch the graph. But what do you notice about it? It's kind of like you took the exponential and you reflected it across the origin, because it's going to be symmetric about the line y equals x. So imagine if you folded your paper diagonally across the origin. And that is because they are inverse functions. So a logarithm is going to have an asymptote at the y-axis. It's never going to cross it, but it's going to get really, really close. And then it's going to extend. Here, I'm graphing with my a value between 0 and 1. And you should notice it's going to be the reflection of the actual exponential, where a is between 0 and 1, because these are inverses. Again, the y-axis is going to behave as an asymptote. So here's a couple characteristics. It always has the point 1, 0, just like your exponentials. They're going to be 1 to 1. If a is greater than 1, it's going to rise. If it's between 0 and 1, it's going to fall. And then my domain and my range, you should notice, are going to be the flip of those exponentials. So to use a logarithm in cases of exponential growth or decay, if I'm looking at a word problem where t is the number of days after a study began, if I want to find the number of mites at the beginning of the study, that's when t equals 0. So my log base 10 of 10 get removed and become 1, and I get 80. For b, to find the number present after 90 days, I'm going to plug in 90. And I'm going to be able to say that that's 2. Why is that 2? Because 100 is 10 squared. So I get 80 log base 10 of 10 squared. The log base 10 and 10 squared are going to cancel out so that I get 80 times 2.